Welcome back to our lecture series on nanostructured materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In our last lectures, we looked at quantum mechanics and confinement. Now we move into atomic interactions that actually hold matter together. Interatomic bonding defines everything: the structure, the strength, conductivity, and optical behavior. Bonding is the foundation of all material science. The type of bonding dictates how atoms arrange themselves into structures, whether that is a crystal like silicon, an amorphous glass, or a polymer change. It also controls the stability of matter, explaining why some materials remain solid at high temperatures or pressure, while others decompose or melt. Different classes of materials, metals, ceramics, polymers, semiconductors, all owe their unique behavior to differences in bonding. Metals are metallically bonded, ceramics are mostly ionic and covalent, while polymers rely heavily on covalent backbones, with secondary bonds holding chains together. Bonding also governs interfaces and surfaces, which is critical for processes like adhesion, wetting, corrosion, and catalysis. These interfacial interactions are central to engineering and technology. At the nanoscale, bonding effects are amplified because so many atoms sit at surfaces with incomplete coordination. This leads to unusual phenomena like enhanced reactivity, different melting behavior, and new opportunities for designing nanomaterials and devices. So, studying bonding is not just about understanding atoms, it is about connecting atomic interactions to real-world properties and applications. Interatomic forces can be broadly divided into two main categories: primary bonds and secondary bonds. Primary bonds are a stronger type and they form the main structural framework of materials. There are three primary bond types. First, ionic bonds. These occur when one atom transfers electron to another, forming oppositely charged ions. The strong Coulomb attraction between cations and anions holds the lattice together. Sodium chloride and magnesium oxide are classic examples. These compounds tend to be hard, have high melting points, but are brittle. Second, covalent bonds. Here, atoms share electrons to fill their valence shells. These bonds are directional and extremely strong, producing rigid structures like diamond, silicon, and germanium. The directionality of covalent bonds explains why these materials are hard but often brittle. Finally, metallic bonds. In metals, atoms release some of their valence electrons into a shared sea of delocalized electrons. The resulting positive ion cores are held together by this electron cloud. This explains the ductility, malleability, and electrical conductivity and characteristic shine of metals like copper, aluminum, and iron. So ionic, covalent, and metallic bonding together account for the primary forces that give solids their strength and stability. Now, let us move to the secondary bonds, which are much weaker than primary bonds, but is still extremely important in determining material behavior. These bonds usually have energies of just a few kilojoules per mole. The first type is van der Waals forces. These arise from temporary or induced dipoles, where electron clouds shift and create a weak interaction between atoms or molecules. Even though they are weak, they are universal, acting in noble gas, solids, liquids, and layered materials like graphite or molybdenum disulfide. In graphite, for example, the strong in-plane covalent bonds hold carbon atoms together, but the weak van der Waals forces between layers allow them to slide, giving graphite its lubricating properties. The second type is hydrogen bonding, which is a stronger dipole-dipole interaction. It occurs when hydrogen is covalently bonded to a highly electronegative atom such as oxygen, nitrogen, or fluorine, and interacts with another electronegative atom nearby. Hydrogen bonding explains why water boils at such a high temperature compared to similar molecules, and it plays a crucial role in biology, stabilizing the DNA, double helix, and protein structures. So, while primary bonds form the solid skeleton of materials, secondary bonds fine-tune properties like adhesion, softness, flexibility, and biological functionality. Ionic bonding occurs when one atom donates one or more valence electrons and another atom accepts them, creating oppositely charged ions. These ions are held together by strong electrostatic or Coulomb attraction. The result is a highly ordered three-dimensional lattice. Because of the strength of these interactions, ionic compounds typically have very high melting and boiling points. Sodium chloride and magnesium oxide are good examples. Ionic solids tend to be hard but brittle. If we try to deform the lattice, layers of like charges are forced to align, leading to strong repulsion and fracture rather than plastic deformation. Electrically, ionic compounds do not conduct in the solid state because their ions are fixed in the lattice. But in the molten state or dissolved in water, the ions becomes mobile and the material can conduct electricity very effectively. So, the key features of ionic bonding are electron transfer, strong Coulomb attraction, high thermal stability, and brittleness. Covalent bonding occurs when atoms share electrons in order to fill their outer shells and achieve stability. Unlike ionic bonding, where electrons are transferred, here they are shared. Covalent bonds are directional, meaning they form along specific orientations in space. This leads to rigid, well-defined structures. For example, in diamond, each carbon atom shares electrons with four neighbors in a tetrahedral arrangement, forming an extremely strong and rigid 3D network. Because these bonds are short and strong, covalently bonded materials often have very high melting points and exceptional hardness. Diamond is a classic example known as the hardest natural material. Covalent bonding also plays a central role in semiconductors like silicon and germanium, which are the foundation of modern electronics. Another example is quartz or SiO2, which forms a strong covalent network, giving it high stability. In summary, covalent bonding gives rise to some of the most important materials in technology, from gemstones like diamonds to the silicon chips empowering our computers. Metallic bonding is quite different from ionic or covalent bonding. In a metal, the atoms release some of their valence electron into a collective pool, forming a sea of electrons. The positive ion cores remain in a lattice while the delocalized electrons move freely throughout the structure. This model explains several key properties of metals. Because the electrons are free to move, metals are excellent conductors of electricity and heat. The bonding is non-directional, which means that when the lattice is deformed, planes of atoms can slide past one another without breaking the bonds. This explains ductility and malleability, while metals can be drawn into wires or hammered into sheets. The presence of free electrons also accounts for the luster of metals, since they interact strongly with light. Bond strength in metallic system varies widely. In alkali metals like sodium, the bonds are relatively weak, leading to soft metals with low melting points. In contrast, transition metals like tungsten have much stronger metallic bonds, making them very hard with extremely high melting points. In short, metallic bonding creates the unique combination of conductivity, ductility, and strength that makes metals so vital to technology and engineering. Van der Waals forces are a type of secondary bonding. They are much weaker than primary bonds but present everywhere. These forces arise from instantaneous or induced dipoles in the electron clouds of atoms and molecules. Even non-polar atoms like noble gases can attract each other for short times through van der Waals interactions. They are universal, acting in all materials, and they play an especially important role in layered materials like graphite and molybdenum disulfide. In graphite, the carbon atoms within a sheet are bonded strongly through covalent bonds, but the sheets are held together only by weak van der Waals forces. This is why graphite layers can easily slide, making it useful as a lubricant and in pencils. Van der Waals forces are also responsible for adhesion and absorption at surfaces, as well as the stability of polymers, soft materials, and many biological systems. While their energy is small compared to covalent or ionic bonds, typically just a few kilojoules per mole, collectively, they can strongly influence material properties. So, van der Waals forces show us that even the weakest interactions can have major effects, especially when we consider large number of atoms and molecules together. Hydrogen bonding is a very special type of secondary bond. It is essentially a stronger, more directional version of dipole-dipole interactions. A hydrogen atom covalently bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine develops a strong partial charge which is positive. This allows it to interact with a lone pair of another electronegative atom, forming a hydrogen bond. Hydrogen bonds are much stronger than ordinary van der Waals interactions with bond energies in the range of 10 to 40 kilojoules per mole, but they are still weaker than true covalent bonds. These interactions are extremely important in both material science and biology. In water, hydrogen bonding is what gives it a high boiling point and unique properties like surface tension. In ice, hydrogen bonds create an open lattice that makes solid water less dense than liquid water. In biology, hydrogen bonding is critical for stabilizing the DNA double helix through base pairing and also for protein folding, where it helps maintain secondary and tertiary structures. So, hydrogen bonding serves as a bridge between weak van der Waals forces and strong covalent bonds, and it is essential for life and many advanced materials. When two atoms approach each other, their potential energy can be described as the sum of attractive and repulsive contributions. The attractive forces, such as Coulomb or van der Waals interactions, decrease roughly as 1 over. The repulsive forces, on the other hand, rise very steeply at short distances due to the Pauli exclusion principle and electron cloud overlap. In the Lennard-Jones model, this repulsion is approximated by a 1 over r to the 12th term, which is mathematically convenient, though more accurately it should be represented by an exponential decay as in the bond-Mayer potential. The result is a characteristic potential energy curve. The minimum of this curve defines the equilibrium bond length R0, where attractive and repulsive forces exactly balance. The depth of the potential well corresponds to the bond energy, which tells us how strongly the atoms are bound together. By analyzing these curves, we can not only understand equilibrium bond distances and energies, but also connect to macroscopic properties such as stiffness and elasticity. Cohesive energy is a measure of how strongly the atoms in a solid are bound together. It is defined as the energy required to separate a solid into isolated free atoms, effectively breaking all the bonds. This quantity represents the overall bond strength in a material. A solid with a large cohesive energy will be more stable, harder to melt, and typically harder in terms of mechanical properties. In contrast, materials with low cohesive energy will melt or vaporize more easily. Cohesive energy directly determines important properties such as melting and boiling points, hardness, elastic modulus, and thermal stability. If we look across different bonding types, we find that ionic solids often have the highest cohesive energies because of the strong Coulomb attraction between ions. Covalent solids like diamond also have very high cohesive energies due to short, strong directional bonds. Metallic solids can vary widely. Metals like sodium and potassium have relatively low cohesive energies, while tungsten and iron have much higher values. Graphically, cohesive energy corresponds to the depth of the potential well in potential energy curve. The deeper the well, the stronger the bonding. Bond length and bond energy are two sides of the same coin. The bond length, often denoted by R0, is the equilibrium separation between atoms, the distance where attractive and repulsive forces balance. The bond energy is the depth of the potential well, or the energy required to break that bond. There is a direct relationship. Shorter bonds are stronger bonds. When atoms are closer together, their overlap is greater, making the bond stronger and the bond energy higher. Conversely, longer bonds are weaker. Strong bonds resist vibrational motion, which means materials with stronger bonds tend to have higher melting points and greater thermal stability. For example, the CC bond in diamond is about 1.54 angstrom, giving it extremely high hardness and a very high melting point. The silicon-silicon bond at 2.35 angstrom is much weaker, leading to a lower melting temperature. Metallic bonds show even more variation. Sodium has relatively weak bonds, while tungsten's metallic bonds are much stronger. So understanding the connection between bond length and bond energy allows us to explain key material properties such as hardness, melting point, and thermal stability. Now let us look at how force varies with distance between two atoms. Force is the slope of the potential energy curve, mathematically written as minus du by dr. When atoms are far apart, the force is negative, which corresponds to attraction. The atoms are pulled towards each other. When atoms come too close, the force becomes positive, meaning strong repulsion due to electron cloud overlap and Pauli exclusion. At a particular distance, called the equilibrium bond length or R0, the attractive and repulsive forces exactly balance. This is the stable bond position. The depth of the potential well and the steepness of the force curve determine how stiff the bond is. Stronger bonds resist vibrations and therefore show higher vibrational frequencies and higher melting points. This force-distance relationship gives us a direct microscopic picture of bond stability. The elastic modulus of a material is directly linked to the curvature of its potential energy curve near the equilibrium bond length. At equilibrium, the first derivative of the slope is 0, but the second derivative, which tells us how steep the curve is around the minimum, determines stiffness. A steep and narrow potential well means strong resistance to bond stretching, which corresponds to a high elastic modulus. That is why a diamond with very strong covalent bonds is extremely stiff. On the other hand, lead has a much shallower potential curve, so its bonds are easily stretched, giving it a very low elastic modulus. In simple terms, the sharper the curve, the stiffer the solid. The thermal expansion of solids can be directly explained using the potential energy curve of bonding. Unlike a symmetric curve, the actual potential well is asymmetric, steeper on the repulsive side and flatter on the attractive side. At low temperature, atoms vibrate only slightly around the equilibrium position. But as the temperature increases, vibrations becomes larger and atoms explore more of the flatter region of the curve. The average bond distance shifts outward, leading to an overall increase in the lattice spacing. This is why materials expand when heated. The extent of this expansion depends on the curvature of the potential well. Strong covalent bonds, like in diamond, show very little expansion, while weaker bonds, like in lead or in polymers, show much greater expansion. The melting point of a material is determined by the strength of its atomic bonding. Stronger bonds require more thermal energy to break apart, and therefore corresponds to higher melting temperatures. Covalent solids such as diamond and boron nitride have very strong bonds, giving them some of the highest known melting points. Ionic solids like sodium chloride and magnesium oxide also have high melting points due to strong Coulomb forces. Metals show a wide range of melting points. Tungsten melts at over 3400 degrees centigrade because of its strong metallic bonds, while lead melts below 330 degrees centigrade because of its weaker bonds. At the other extreme, van der Waals solids such as argon, krypton, or solid xenon melt at very low temperatures, sometimes close to absolute zero, because their intermolecular forces are so weak. Overall, the melting temperature scales with cohesive energy, and this is a useful way to compare different classes of materials. When we move from bulk materials to nanomaterials, bonding changes significantly. One of the key reasons is the very high surface to volume ratio at the nanoscale. In a nanoparticle, a large fraction of atoms lie at the surface, and these atoms are undercoordinated. They have fewer neighboring atoms to bond with compared to atoms inside the bulk. These undercoordinated atoms often have dangling bonds, which makes them more reactive. This is why nanoparticles can be excellent catalysts even if the same material in bulk form is inert. At the nanoscale, bond lengths and bond strengths are also modified. This leads to phenomena like melting point depression, where smaller particles melt at much lower temperatures. Electronic and optical properties also change dramatically. For example, gold nanoparticles show vibrant colors due to size-dependent bonding and electronic effects, while bulk solid gold simply appears metallic and shiny. Thus, bonding at a nanoscale is not just a scaled-down version of bulk bonding, it is qualitatively different and governs the unique properties of nanomaterials. Two-dimensional materials such as graphene and molybdenum disulfide have a very unique bonding structure. Within each layer, the atoms are held together by strong covalent bonds, which make the layer itself extremely stable and durable. However, the layers are stacked on top of each other and are held together only by weak van der Waals forces. This large contrast in bonding strength makes it possible to peel off or exfoliate single layers from the bulk material. That is why graphene can be obtained simply by mechanical exfoliation, and MOS2 can also be separated into few layers. This property has opened the door to flexible electronics, wearable devices, and next-generation nanotechnology. While the in-plane covalent bonds provide stability and strength, the weak interlayer bonds enable flexibility and unique applications. When atoms are inside a crystal, they are surrounded and fully coordinated by their neighbors. But at the surface, many of those bonds are missing or broken, which raises the system's energy. This is why the surfaces are always higher in energy compared to the bulk. To reduce this excess energy, surfaces often reconstruct, change their structure, or absorb other atoms and molecules. This principle drives key processes like nanoparticle faceting, where particles adopt shapes that minimize their surface energy, and thin film growth, where surfaces evolve to lower energy configurations. Surface energy is also critical in catalysis. High energy surfaces sites can be highly reactive. Overall, surface energy explains why materials minimize exposed area, why nanoparticles adopt special shapes, and why surface-dominated nanomaterials often behave very differently from bulk solids. The melting point of nanoparticles decreases as their size decreases. This effect is explained by the Gibbs-Thomson relation. According to this relation, Tm of R equals Tm of infinity multiplied by within bracket 1 minus C over R. Here Tm of R is the melting temperature of a particle with radius R. Tm of infinity is the bulk melting temperature and C is a material constant. This equation shows that as the particle radius becomes smaller, the melting temperature drops significantly. The reason lies in surface energy. Nanoparticles have a very high surface to volume ratio. This means that many atoms are at or near the surface with broken or weakened bonds. These surface atoms destabilize the solid phase, making it easier for the particle to melt. That is why nanoparticles can melt at hundreds of degrees lower than their bulk counterparts. This effect is extremely important in nanomaterial applications such as catalysis, sintering, and nanoelectronics, where stability and processing conditions are directly influenced by particle size. Carbon is one of the most versatile elements in nature, and its bonding is the reason for its versatility. In diamond, every carbon atom forms strong covalent bonds in 3 dimensions, producing a rigid and transparent crystal. This makes diamond extremely hard, an excellent thermal conductor, but an electrical insulator. In contrast, graphite has the same carbon atoms but arranged in sp2 hybridized hexagonal sheets. The bonds within each sheet are strong, but the layers are held together only by weak van der Waals forces. This gives graphite its softness and lubricating properties and also allows it to conduct electricity along the sheets. When a single sheet of graphite is isolated, we obtain graphene. Graphene is just one atom thick, yet is stronger than steel and highly conductive, both electrically and thermally. Thus, the same element carbon can be a super hard insulator, a soft lubricant, or a wonder material for modern electronics, depending on how its atoms are bonded. The mechanical behavior of a material is closely tied to the type of bonding between its atoms. Covalent bonds are very strong and directional, which make materials like diamond extremely hard but also brittle, since bonds cannot easily rearrange when stressed. Metallic bonds, on the other hand, are non-directional, allowing atoms to slip past each other. This gives metals like copper and aluminum their characteristic ductility and ability to deform without breaking. Ionic solids such as sodium chloride also have strong bonds, but because the arrangement is highly ordered, any slip brings like charges together, causing fracture, making them brittle like ceramics. Finally, van der Waals solids such as graphite or polymers have very weak interactions, leading to softness and poor mechanical strength. Bonding in solids directly determines the electronic band structure and therefore the electrical properties of the materials. In metals, metallic bonding creates a delocalized electron sea where valence and conduction bands overlap. This means electrons move freely under even a small applied voltage, making metals excellent conductors. In covalent solids, the situation depends on the size of the band gap. Materials like silicon and germanium have small band gaps, typically less than 3 electron volt. Electrons can be excited across this gap with thermal or optical energy, giving these materials their unique semiconductor behavior. On the other hand, covalently bonded solids like diamond or silicon dioxide have very large band gaps, greater than 5 electron volt. Here, electrons remain tightly bound and the material behaves as a strong insulator. In ionic solids such as sodium chloride, electrons are strongly localized around ions, and the bonding results in wide band gaps. These materials are almost always insulators under normal conditions. Thus, By looking at the bond type and the resulting band structure, we can predict whether a material will be a conductor, semiconductor, or insulator. The optical behavior of a material is closely tied to its bonding and its band gap. If the band gap is wide, as in diamond and many other insulators and oxides, visible light cannot be absorbed and the material appears transparent. When the band gap is narrow or intermediate, as in semiconductors like cadmium sulfide, zinc oxide, or gallium arsenide, visible light is absorbed. This absorption gives rise to distinct colors. In metals, there is no band gap. The free electrons respond to light strongly, leading to high reflectivity and in some cases plasmonic effects. This is why metals like gold and silver have their characteristic shiny appearance. Finally, even small changes such as defects or intentional doping can tune the optical absorption of a material. This is how we engineer semiconductors for LEDs, lasers, and solar cells. So bonding and band gap together explain whether a material is transparent, colored, or reflective. To wrap up, bonding truly forms the foundation of material science. By understanding how atoms interact, we can predict not just the structure but also the stability and function of materials.